Hi everyone, thanks for coming along. We've got Arnaud coming down from Cambridge. He's about to join Imperial also as a postdoctoral fellow as well. You originally had a civil engineering background, I believe, from Ottawa, and currently a postdoc at Cambridge. I'll leave the rest up to him to introduce his talk and the cool engineering applications you'll show us.
Fantastic, thank you very much, and thank you for the invitation as well, and thanks for coming to the presentation. So I would like to take this opportunity. I just want to talk about some work that I've been doing over the last couple of years. So the things that I've been trying to develop over the last few years are things that I'm going to be getting into more depth over the next coming years as I'm joining Imperial. So as Pishan was mentioning, I'll be at Imperial as a research fellow. And the idea is to take some of the methodology that I've developed over the last couple of years, which is mainly around machine learning and data assimilation and model calibration, and try and adapt it to try and solve challenging problems in engineering, particularly related to problems in infrastructure. So in a lot of contexts with infrastructure, civil infrastructure, we have these assets that that essentially have been deployed and they've possibly undergone some kind of transformation, some changes as they've been exposed to their operational environments. And the idea is that if we would like to predict the future behavior of these assets as they're when they're going to be exposed to new loading and new demands, we need to have good models that are going to be able to predict that kind of future behavior. And we already have very good models in terms of finite element models, which tend to have a very good description of the physics at play, but often we don't have a good calibration, a good alignment between the numerical models that we have and the physical assets that we have. And so what I'm interested in is this model calibration task, which is how do you align your numerical model with your physical assets such that that allows you to both, I mean, that's of intrinsic interest because it can allow you to investigate things non-intrusively, the internal properties of your assets, but also it can help you predict the future behavior of that asset by using the physics that you know that's in your model. Is this this is not the arrow or okay, perfect. So what I want to be doing is I'm going to introduce the challenges and opportunities of big data in engineering for model calibration. So I'm going to be talking about scenarios in which you have access to very large amounts of data potentially. Perhaps your structure is instrumented and you've been measuring data for a long time, but I'm going to be talking mostly about the context where you possibly have data from many different physical systems, and you would like to pool that information together to learn something more informative than if you had access from a single physical system. So I want to introduce kind of the core methodological developments on this line that I've been working on, showcase some applications, and the idea with showcasing the applications is mostly that if you see problems that are related to things that you're interested in, and you think there'd be some kind of parallel that could be of interest to explore, please reach out. And then I'm going to talk about basically where I'm going to be going with this over the next couple of years of as I develop this research program. So first off, I want to talk about model inference. And I just want to kind of get on the same page as to what we mean by model inference. So that the forward problem is essentially answering the question, what is going to be the behavior of a given physical system if I had a set of parameters, and how is that actually going to be mapping forward to some particular behavior of a physical system that I have? So for example, a forward problem would be the solution to a finite element model, where I have some particular set of parameters, maybe material properties in my finite element model, and I'm going to solve my forward model, and that's going to tell me what the behavior of that system is under that given physics. Now, the inverse problem asks what the reverse question. Basically, if I can observe some behavior of my physical assets, can I work out what were the parameters of my model that were the likeliest to be responsible for the observations? So this is this model calibration task where we try and align our forward model with the reality that we want to observe by matching observations with outputs of these models. So here I'm going to set some notation. The Z is going to, so calligraphic Z is going to denote the space of parameters. So that could be any possible parameter configuration that I have. That's going to be that space calligraphic Z. F dagger is going to be the solution operator for a PDE that describes the physics of interest. So if I have something like I'm interested in elasticity, Z will be like material properties. F dagger will be my finite element solver, which is my elasticity solver that outputs displacements, and that will be the space U, which will be the space of solutions for that forward model. And then G is going to bring me to my observable space. So this is where actually I related the output from my model to what I can actually measure. So that would be like placing sensors on a beam, and when I observe the deflection, what I'm measuring actually is just a set number of locations where I actually register what the displacement was. And the space of all possible observations would be that space Y. And so the arrows going that direction are basically the forward problem, and anything going in the other direction would be considered an inverse problem. So inverse problems is a very established methodology where typically I'll assume to have some data. So this is kind of like the most classic setup for solving inverse problems, where I have some noise. Basically, my data is equal to Y here. That would be the vector of observables. Again, in the example of the beam would be like the specific locations in which I've observed displacements. And then my F dagger is mapping forward a particular variable Z to the solution of the PDE, which describes that deflection of that beam. And then Psi here denotes additive noise. So perhaps I have some corruption when I measure my my displacements, and that I'm going to assume is drawn from some Gaussian. And that's kind of like the standard setup for a lot of inverse problems. And the way in which solving these kinds of inverse problems is typically approached is by doing some kind of least squares fitting, where I'm going to take the output of my model as I observe it, and I'm going to try and match that as closely as possible to my observations. And so I'm going to minimize that kind of square distance between my observables and the output of my model. But that will typically be opposed, and I'll subject that to some regularization, which might basically impose what I think would be the likeliest parameter before I've actually seen any data. So that's kind of like the core of most inverse problems or model calibration methodologies. And of course, you can be statistical about this with a Bayesian approach, and in which case you would essentially have probability distributions that are wrapping around each of these terms, and the output of this procedure would be a distribution on parameters of interest. So that would be kind of like the Bayesian approach to this. But I want to talk about a context in which I have access to data from more than one physical system. So instead of having a single physical asset, I have a fleet of physical assets. So instead of having one beam that's been manufactured, I have 1,000 beams that have been manufactured. And what I'm interested in recovering is not just information about any one particular physical asset, but I would like to learn information about the population of assets as a whole. So here, the way that I've written this down is saying that I've got the same data generating setup as before. This Y is equal to G of F plus Xi. However, now everything is indexed by N, this variable N, which runs through from 1 to capital N. And this is indexing the multiplicity or the multitude of physical systems from which I have access to data. I'm going to assume that my Xi, my corrupting variable, is drawn from some noise distribution, which is P dagger Psi, because that's kind of like the ground truth that I don't have access to, or that I may have access to, depending on the context. And Z is going to be drawn itself from its own probability distribution. And the object of interest is that probability distribution. So that's kind of like saying I have a manufacturing process which is generating a certain distribution over Young's moduli for a particular, for essentially for my steel, for my materials, and then I'm making these assets out of this material, and then I'm going to observe physical behavior of these assets, and I'd like to learn what was the distribution on the material properties for the population as a whole. And that's of intrinsic interest in terms of understanding possibly the manufacturing process, what the manufacturing process is actually implying on the material properties, but it's also of interest if these have been deployed in terms of understanding the distribution of degraded material properties, which might tell me something about the environment, the relationship between the materials and the environment. So that's basically the motivation for looking at these problems. So when this capital N is very, very large, we can adopt thinking from machine learning. And the idea is essentially to approximate the data generating mechanism as a generative model. So many people now are familiar with generative models. Typically, they're these models where I can give some prompt, and then the output would be some image that is somehow related to that prompt. And the way typically that these things work is that you have a very large corpus of data, and what you're going to do is you're going to try and model the data generating distribution as the object of interest itself. And now you can query that model and generate new data from that. And that would be these new images that the generative model can output. So here we're going to try and adopt a similar kind of approach, but of course we're in a different context where the relationship between the variables of interest are mediated by physical process. So I somehow have to incorporate physics into my generative model to be able to recover something that's physically interpretable and physically meaningful. Now, there is precedent in trying to solve the kinds of problems that I've outlined in terms of kind of classical statistical methodology, in terms of hierarchical Bayes methods. But if you're interested in these, we can talk about what are their shortcomings and why what we're going to propose addresses some of these shortcomings. So the way that we're going to do this, we're going to try and pose this generative model in a mathematical way by essentially talking about transformations on distributions. So I've got that PZ, which is going to be that distribution on the parameters of interest. And this sharp here, sharp with these, the G and F, which are functions, which are in front of it, describe taking the Bayes distribution on properties of interest and pushing them forward through my model and then pushing them forward through my observation process. So here I'm talking about looking at a distribution of interest and transforming that entire distribution of interest to a distribution of observables. This is in contrast to the kind of classic one-to-one setup where I have just one physical setup where I have one parameter, I solve that forward and I look at the output. Here I'm transforming distributions of parameters and looking at the implied distribution on observations from that model. So that's the model. And then the second thing we need is data, because we want to align a model with data. And here we're going to talk about the data as a data distribution. So I'm going to take all of the observables that I have for a series of physical systems, and I'm going to collate that and say that that is a single distribution. And what I want to do is I want to match my generative model to that data distribution, but not on a point-by-point basis, but at this distributional sense. So in order to do this, to match that generative model with my data distribution, I'm going to use a statistical divergence, which basically it's a tool that allows me to measure the distance between, or the difference, or the discrepancy between a data distribution and my generative model. And I'm going to try and minimize that such that they align. And hopefully by this alignment process, I can learn something of interest on the distribution of parameters of interest. And I'm going to be subjecting this to regularization because that might help make the problem more well posed in some context, but it's not always necessary. So this is kind of like a technical note on what choice of divergence we actually want to be using. So we want something that's ultimately, this is going to be a computational scheme. So we want to have statistical tools that allow us to compute the quantities that we need very efficiently. And we're going to be making use of kind of these automated ways of computing gradients through models called automatic differentiation, which is kind of the backbone of modern machine learning, or the workhorse of modern machine learning. And the idea here is that we're going to be using a easy to compute, well-defined divergence to compute the distance between the output from our generative model and our data distribution. Now, if you're interested in implementing these things, there's some specifics that go into it. I'll kind of skip over those, but if you're interested, please do ask questions about that. So the idea now is that we can learn a lot of things about collections of physical systems by doing this distribution matching approach. We can possibly learn more than if we did point-by-point matching, as what would be like the standard methodology. So we can learn about the model parameter distributions, which is PZ. We can possibly learn about the noise distribution as well. So that might be something that is to do with the sensing the sensing equipment that I have, and understand what is the distribution on corruptions that my sensing equipment induces on my observations. And I can also possibly learn to approximate my expensive to evaluate finite element models. So that's something that is going to be necessary to tackle much more difficult problems, where we want to possibly have a much more cheap to evaluate approximation to an expensive finite element model with something like a machine learning surrogate that's going to approximate the solution map for that solver, but somehow kind of retains the key aspects, the key properties that we want from our solver. And then I'm going to talk a little bit about how this can be used to learn useful latent representations of PDE solutions, but that's kind of a slightly adjacent topic. So the applications that I'm going to be discussing are porous medium flow. So that's primarily what describes groundwater seepage. Damped elastodynamics, which is used a lot in structural dynamics. I'm going to talk about Lorenz 96 single and multi-scale models. These are simplified models of atmospheric dynamics. But that's really the idea, is that these are kind of like the canonical or the first step in dealing with chaotic dynamics. There are lots of different situations in which in engineering we deal with chaotic dynamics, and this is kind of like the prototypical example. And then I'm going to talk about homogenization. That might be of relevance to people that are interested in soil mechanics as well, basically through the idea that we can link fine material microstructure to bulk mechanical properties, then we can apply distributional inversion to these kinds of problems to learn something about microstructure from the observation of bulk mechanical properties. And then I'm going to talk a bit about Helmholtz resonance and Reynolds average Navier-Stokes, but those again are slight asides for the main topic. So I'm first going to discuss this first work that we've done a few years ago with my collaborators Dennis, who's based here, my postdoc supervisor Mark, and Andrew Stewart, who's based in Caltech. And this is kind of like the first paper that we did in this, trying to establish this methodology for physical systems. And here we work with the steady state porous medium flow, or the Darcy flow equation, where here we have the PDE that describes the relationship between the material diffusivity, which is Z, or the permittivity, and how that then relates the kind of like the resistance of the material to diffusion to the piezometric pressure head at various spatial locations. So here, D is a physical domain, and it's going to be describing, or I have some spatially varying material properties across that spatial domain, which would be like different kinds of soil porosities at different locations. And then I'm going to be using this equation to describe the way in which water seeps across this 2D domain, or this n-dimensional domain. So and then here F dagger is going to be the map that takes my parameters Z to U, which is that fine element solver essentially that I can use to solve these equations. Now what I'm describing here is basically a mathematical description of a relatively simple generative model for material properties, but the idea is that I have two material types. I've got this, say, sand type A and sand type B. And they're going to be physically configured in space in a random way. So I kind of have like random interfaces between the different material types. And what I would like to learn about is the frequency or the spectral information that describes how often I'm switching from one material type to another in my random domain. So say I've got like physical domains, so actual like material soil fields that exist somewhere in nature. I've got lots of examples of them. They're going to have lots of different materials in them, and they're going to be in a geometric layout that is kind of varying across space and varying across physical systems or physical fields. And what I would like to learn about is kind of like the spectral information about how rapidly one material changes from another. So it's kind of like an expression of how variable my soil is in various locations. And so this is kind of just a description of the spectral information that I would like to learn. These are describing modes of a spectral expansion that parameterizes the random field over the material parameters. I realize it's a bit of a mouthful, but basically the material properties, or my actual soil looks like A. In the 2D case, the top line is the 1D case, which is a bit less physically informative in this case, but the bottom one essentially describes a physical field where I've got this first material type and the second material type, and they're arranged in this random manner. And what I want to be learning about is essentially information about the frequency at which I transition from one material to the other by looking at large collections of realizations of the solution to the steady state flow equation for this particular problem. So if I had access to data from only a single physical field, this would basically be a completely ill-posed problem. I wouldn't be able to tell you anything about how quickly materials are changing from one setting to another. However, if we look at the problem from a distributional point of view, and we have a large collection of these physical systems, we actually may be able to recover that information. So here, what I'm learning essentially through this kind of matching data distribution with generative model approach is that spectral information, which is lambda, and then I'm also being able to learn kappa plus and kappa minus, which are the individual material properties of the two different material types. So we can both learn about the different material types that are in the series of physical fields that I have, but also having access to information that is inherently distributional, which is not something I would be able to do very well if I only had data from a single physical system. So now I want to talk about essentially what happens when I have varying amounts of data for solving these kinds of problems. So here, the different colored curves represent the number of physical systems to which I have access to data when I do the inference. And then the x-axis essentially is the computational cost of running the algorithm. And if I have access to a data from a single physical system, so n is equal to 1, I'm on the blue curve. And what I want that blue curve to be close to the dashed line, which is the ground truth. This is all synthetic experiments, and so we know what the ground truth is. And you can see that if I have access to only one physical system when I try and carry out this inference procedure, I don't do a very good job at all of recovering the parameters of interest. And as I increase the amount of physical systems to which I have access to data, I do a much better job at recovering the ground truth parameters. But the important thing is that essentially there's a saturation point at which increasing the number of samples necessary to evaluate the loss function, which is what this x-axis is, which is the cost of running the algorithm, saturates relatively quickly with respect to the amount of data that we have. So here we have a methodology that does this distributional calibration. However, we've decoupled the cost of running the inference with respect to the amount of data to which we have access to. So if I had applied more classical statistical methodology to this, as I acquire more and more data and more physical systems, the cost of running the algorithm tends to grow very rapidly. Whereas in this case, we've actually decoupled the two, which is significant for problems in engineering where we might be facing a very large amount of data. If we actually want to have algorithms that are tractable for those scenarios. So now I've talked about, replacing, calibrating our generative model and learning something about the parameters of interest if we have access to a finite element solver. But we know that finite element solvers can be very expensive to evaluate when you want to evaluate it many times. So for the slides that I showed previously, I actually needed to evaluate a finite element solver 1,000,000 times. It happens that the problem was very easy to solve and was parallelizable on the GPU, so it only took a couple minutes to run. However, if I'm dealing with more challenging realistic engineering problems, I can't rely on evaluating a finite element model 1,000,000 times, especially if it takes maybe a minute or something to run. So the idea now is that we would like to replace our expensive to evaluate finite element model with a surrogate model, which would just be like a neural network approximation to my finite element model. However, I would like this surrogate model to be accurate. Obviously, I don't want a globally accurate surrogate model. I don't want a surrogate model that will replace every single finite element model that can exist, because that would be far too expensive to train in the first place, and the end surrogate might be very expensive to evaluate. Anyways, what I would like is I would like to have a surrogate model that is tailored to the data or to the parameter distribution of interest that is relevant for the inference task. So I have this kind of chicken and egg problem where I want a surrogate model, a machine learning replacement to my finite element solver that is accurate specifically for parameter values that give rise to my observations. So how do I actually tie these problems together where I get a surrogate model to be efficient for a quantity that I do not have direct access to, that I have to solve an inverse problem for? And the idea is that I'm going to write down an objective function which just tells me for a given generative model, how good is my surrogate model at capturing the physics for parameters that are drawn from that particular generative model. So this would be something like a residual, so a physics residual. So that's if I take my PDE and I put everything on one side, I get a residual. That can essentially tell me how good my surrogate model is at capturing the physics. And what I'm going to do now is I'm going to tie together the model calibration and surrogate modeling tasks together jointly. And the way that I'm going to do this is by using something called bi-level optimization, where bi-level optimization is a method by which you can couple an upper level problem, which is going to be a regularized data fit problem, to a lower level problem, which is essentially really a condition. This is basically saying that I want to fit my data with my model, but when I do that, I want my surrogate model to be accurate for the physics that I think is with respect to the parameters that I think are relevant for the data fit problem. So I have this kind of nested problem where the upper level optimization tries to fit the data, and then I've got a lower level optimization problem which tries to make sure that my surrogate model is accurate for the particular inference values that I've got in my data fit. This is about how to implement finite element residuals efficiently for the GPU. If you're interested, we can talk. But basically, the bottom line is that our algorithm works now as it did before. It takes a little bit longer to converge, but the important bit here is that I'm never actually evaluating my finite element model or solving my finite element model. I'm just using physics residuals to check whether or not the output for my surrogate model actually respects the physics that I would like to impose. And then on top of that, I'm running my parameter inference. So I'm doing this problem where often people will first train a surrogate model and then afterwards we'll try to solve inverse problems with that. Here we're doing this in a combined procedure. So that was kind of like that first piece of work where we kind of tried to establish the methodology and worked with this porous medium equation. And now I want to talk about kind of the second piece of work that we did after this, which was to address two major challenges in what we'd done previously. In what we'd done previously, we assumed that we knew what the corruption was on our data. So we assumed that we knew what the noise distribution was. That's not necessarily very realistic in a lot of engineering contexts where we're just given some data and we just kind of have to assume that there's some physics underlying this and that we have to assume that there's some kind of corruption. Well, here the idea is going to be to try and concurrently learn about the noise distribution whilst we're carrying out our inference procedure. And also, before, the way in which the surrogate model was learned was by using physics residuals. So if I actually know what the PDE is, I can write down what a good residual formulation for that PDE and work with this. But oftentimes, people tend to impose their physics with the solver that they already have. So a lot of companies will already have a solver, they trust their solver, and their solver will not typically be a single PDE that you can write down very cleanly. It'll be loads of switches and loads of things happening in there that describes lots of different contexts in which things can move and change. And so what we would like to do is be able to have a surrogate modeling strategy where we don't base ourselves off of physics residuals, but we can incorporate some pre-existing solver as a black box model. So we can query for a parameter that I put into my model, what's going to be the output, and I would like a surrogate model to accelerate that computation. So the way in which we do the surrogate modeling now is essentially by doing active learning, where we have now the parameters of our surrogate model, which are phi, are going to be trained on the fly, but in a more kind of classic supervised manner, but where I'm collecting, as I do my inference, pairs of inputs and outputs from my black box model to be able to train that surrogate model. And that's going to be replacing the residual that I was using previously. And then the idea is that we would like to learn the deconvolution problem, which is basically disentangling the noise distribution from the underlying physical signal for problems that look like this. So this is the 1D Darcy flow equation, and the dashed line represents solutions to the PDE, and the dotted lines represent data that I've collected, which are noisy perturbations of the underlying PDE solution, where I assume that the physics is understood. And the problem is, well, can you learn something of interest about the kind of the noise corruption? And here you can see that the noise corruption is highly correlated in space, which makes things very difficult. And we apply this to problems in elastodynamics, where maybe I have a beam and I can measure accelerations at various locations. And it happens that whenever I have measurement noise, the measurement noise is correlated from one beam location to the next. Maybe there are external excitations that are causing miscomputations or misacquisitions in data. And the idea is that I would like to learn about the distributional material properties as before, but also the noise distributions concurrently. And I mean, obviously, I'm not explaining what's going on here, but basically this is showing the loss and convergence to the parameters of interest towards the ground truth for the parameters of interest. And yeah, so that's kind of saying that we're both learning a good surrogate model, whilst we're also learning to fit our data distribution that happens to do a good job at recovering the parameters of interest, both for the physical system and for the noise distribution itself. Okay, now I mentioned before Lorenz 96, the multi-scale model, which is essentially the canonical example for chaotic dynamics, which do occur in various settings in engineering. And the idea is that we can apply this methodology to look at, not to track the trajectory of these kind of chaotic dynamics, but we can look at time averaged quantities of these chaotic dynamics. So if I've got sensors that are measuring the behavior of my physical system, and I can somehow collect time averages of that behavior, can I use that information to do model calibration distributionally? And the answer is yes, and it works reasonably well. And we can use the noise estimation kind of apparatus that we developed in this methodology to learn the covariance of those time average statistics, which happens to be very useful for the inference that we're trying to carry out. Yeah, so I'm going to take a little. So now we move on to problems in homogenization. So I don't know if people are familiar with the theory of homogenization, but basically the idea with homogenization is that materials often have very complicated microstructures. So there's a very small micro level layout of physical layout of different kinds of materials that make up some bulk aggregate material. And the mechanical properties and the physical layout of the constituent materials in the microstructure dictate the average bulk mechanical properties of my material. So if I think about steel, when it cools down forms crystals, and each crystal, depending on the way it was formed, might have slightly different mechanical properties. And the collection of all these and the physical layout will dictate the bulk mechanical properties of the overall material. And it is of interest to learn from macroscopic mechanical properties what is the microstructure that gave rise essentially to that bulk mechanical property. And that might tell you something about how your materials are degrading over time. And might also tell you something about your manufacturing process. Obviously, people know how to investigate microstructure, but typically that requires very intrusive methodology where people will take small ingots and then they'll etch them and all these kinds of things. What we would like to do is we would like to look at very large collections of measurements of bulk mechanical properties for materials, apply distributional inversion to those large collections of bulk mechanical properties to learn something about the statistical properties of the microstructure. So here now we're casting the methodology that we've developed, this distributional inversion methodology, to solve problems related to materials via the theory of homogenization. So obviously, homogenization itself is an averaging map. So it takes a very complicated microstructure and averages those properties in a systematic way to get the bulk mechanical properties. But distributionally, it happens that some problems actually are invertible. So there exists one-to-one correspondences between microstructures and bulk mechanical properties at the distributional level. So here, this is trying to be a little bit more concrete. Imagine that I've got a 1D piece of material, and I've got 3 different material types, A1, A2, and A3, and their layout spatially can change. So it's variable spatial layout. So here on the left, I'm showing these same volume fractions plots, which are basically these 4 different materials where the microstructure is kind of randomly laid out, but each material type has the same volume fraction. When I apply homogenization theory to this kind of material layouts, I get a single bulk mechanical property for all of these different physical layouts. However, if the volume fractions of different material types is random, what I observe when I homogenize a collection of these kind of random microstructures is I get a distribution on bulk mechanical properties. And you can see that this distribution on bulk mechanical properties actually has quite a lot of information in terms of the shape of the distribution. And it turns out that that shape of the distribution tells us a lot about both the distribution on the volume fractions for the different material types, but also the individual material properties A1, A2, and A3. So that was the 1D case. We apply this to the 2D case. So here, this is the 2D case where we have a Voronoi description of different material layouts. So this is used a lot in modeling steel microstructures. And the idea is that if I have these random Voronoi diagrams, they'll induce random homogenized coefficients that have a very specific distribution in the configuration space. And I can use that distribution to learn things about the way in which these Voronoi diagrams were constructed, and also the individual material properties for each of the cells in my Voronoi diagrams. Now we've extended this to the case in which I don't have access to IID data, so I don't have access to completely independent measurements, but possibly have a very large specimen, and I can query the mechanical properties at various locations. So my data will be mildly correlated. Essentially, this was trying to emulate a realistic data acquisition scenario, and so we've applied our methodology to that kind of problem as well. So this is the last kind of application area that I want to talk about, and this is a slightly different setup. So here the setup is that I have access to data from physical systems where the geometry of the individual physical systems matters a lot. So essentially, the geometry of the physical systems will dictate the way in which physics is taking place on these objects. So the examples that I have for this are essentially wind flow or airflow, sorry, around a wind turbine blade. So here the geometry of the wind turbine blade will dictate a lot about what the flow is actually doing around it. Well, I determine it nearly completely. I also have boundary conditions, and I have things like viscosity that are going into the model. But the idea is that if I've got data, maybe it's simulation data from lots of different geometries that represent solutions to physical processes that relate to those geometries, can I learn a highly informative distribution on the physics that's taking place given a particular geometry? So if I give you a data set of wind turbine blades and airflows that are going over the wind turbine blades, can you learn a generative model about the physical process that relates the geometry to the physics in such a way that if I give you a new geometry that's not in the data set, you can then tell me what is a very likely physical realization of the process that's in your data set, but related to this new geometry. And the way that we're using this is as a highly informative prior for solving Bayesian inverse problems as a downstream application. So here the idea is that I'm only going to be measuring with my new kind of physical asset, my new geometry, pressure along the surface of my wind turbine blade, and I want to be using my highly informative prior to do a full field reconstruction of the pressure and velocity field around that wind turbine blade. The idea is that this is a very ill-posed problem. Many possible flow fields would have given rise to those pressure measurements, but I'm using all the information that I have in my data set of related geometries to hone down and narrow down the inference and actually be able to recover something meaningful. So this was kind of like a fun toy example that we did. This is applying the same methodology to resonance equations on surfaces of vehicles, mostly just because they have quite complex geometries, but there are going to be other scenarios in which complex geometries can be incorporated in this framework. The idea here is that I've got data of observations of the resonance on the surface of these vehicles that are induced by some forcing, some localized forcing. So here on the bottom row, I've got this forcings, and on the top row, I've got the resulting resonance that's being brought out from the geometry by this forcing. And the idea is that if I now give you a new geometry and I only give you small number of sparse observations of the resonance, can you reconstruct the resonance field, which is of interest, but also can you localize the source of the forcing? So can you actually tell me which part of that geometry is actually being forced? So this is a toy example with very simple geometries because we had access to a data set of these kinds of simple geometries, but the idea, especially in the fellowship, is going to be to extend this to infrastructure problems, where I might want to investigate properties of the vibration of structures by using these kinds of highly informative prior distributions. And this kind of going in that direction, this is an example where we did the same thing, but we have wind flow around terrain. But we can imagine other scenarios where instead of wind flow, it's another kind of physical process from which I would like to kind of collate information that pertains to the geometry as well. So yeah, so that was a very, very quick overview of what I've been working on over the last few years. And the idea with what I'll be doing, hopefully doing when I join Imperial, is to look in particular at problems related to geometry and how we can leverage geometry from lots of physical systems in order to learn about physical processes that are taking part in this geometry, but also help us predict the future behavior of assets that will have different but related geometries. It has to do with collating information from long time series data where the dynamics may be chaotic and where most data assimilation methodologies tend to fail. And lastly, on learning better material models by looking at the homogenization procedure and the distributional inversion that we can do in the context of homogenization. So this was funded by EPSRC as part of the ROSIPS project. Yeah, I'd like to take any questions if you have any questions.
Any questions on? There's a lot more actually.
Yeah.
So you've covered a lot of applications that are interested that are contiguous to ours. Although we obviously are quite removed from this type of work. But we spoke halfway through your presentation about using black box surrogates that you know. So let me walk one step backwards. So part of the problem is when people go and say, well, I've introduced my physics informed networks and things like that, they always give an example where the whole system is described by people, right?
Yeah.
And you yourself said, I mean, sometimes this isn't the case. So in our case, this is never.
Yeah.
Like in our problems, this is never the case. It's a lot more complex system with a lot of variables. I'm even going to leave out the noise and uncertainties and stuff like that. And so I wonder if you could give us a little bit more outlook on how we could use this approach to train your survey, and what's unclear to me is what kind of procedure is there that outputs a surrogate and an estimate of the parameter, where your surrogate is a much more complex system, like a big FE model.
Yeah.
There's all sorts of models. I don't know if you could comment on this. I know it's a bit unfair because this is a huge problem, but if you could give us a couple of pointers of difficulties associated with this and what we could expect.
Yes. Yeah. I mean, it's a very I think it's a very realistic and a very interesting way of looking at these kinds of surrogate modeling problems. So for me, when I think about what is a good surrogate model, I don't tend to think about a surrogate model as being good removed from the actual scenario in which I would like to use that surrogate model. So I don't want to think about, I mean, a lot of people, I think in operator learning, think about scenarios in which, well, I have this PDE, I'm just going to learn a surrogate model for that PDE, and that's kind of done. But the reality is that trying to learn a globally accurate a globally accurate surrogate model that replaces all possible PDE solutions or PDE solves is quite unrealistic. So I think of a surrogate model being a good tool to replace a numerical solver, specifically when it relates to a class of physical settings in which I would like to evaluate it. Basically, what I'm trying to get at is that obviously the surrogate model is going to be an input-output kind of machinery, and I want to make sure that the inputs to my surrogate model relate to the inputs that I want to be evaluating my surrogate model in practice for. So that's why I think that doing the model calibration task or doing the model alignment task goes very well with the problem of trying to develop a good surrogate model, is that when you're in the model calibration setting, you have access to observational data. And so what you want is a surrogate model whose outputs are going to be close in some sense to the observational data that you have, but by respecting the physics fully, right? You have your, do you want to add something to that? Or?
Yes, I can understand I think I understand the essential concept. I'm just trying to map that to our activities.
Yes.
So for example, let me give you an example of something currently doing we have this class of problems where we did a great big excavation, right? And we have this movement of the wall. And this movement of the wall that supports excavation is only computable by an explicit finite element analysis. Nothing else works.
Yeah.
And in the process that you have described, where do I get to call the finite element solver? This is the thing that I have.
Yes.
When do I get to call it, and how do I get to call it, and how often do I get to call it?
Yes.
And what am I trying to get out of it?
So
because just to say that when we do a survey for this wall, what we do is we essentially call this we call this solver 1,000 times.
Yeah.
We look at the response of the wall, and then we do the classical surrogate task of creating a neural network that relates the inputs to the outputs through that database we create.
Yes.
What I really don't see here yet, that I didn't capture that yet, that's what I need help with, is where do we get the FP to come in? And,
Yes.
And
so here what I've got up is the bi-level optimization scheme that I was talking about, where the upper level problem tries to match the output from your physics to the data.
which is independent of So whether you have a surrogate,
which is independent of whether or not we have a surrogate. So we could do that with a finite element model. What I'm going to do is I'm going to write a lower level problem, which is going to relate input-output pairs to the observables. So basically, what I want is I want a surrogate model. So this is where I'm going to essentially train my surrogate model. Is going to be in that lower level loop, and I want my surrogate model to match the input-output behavior of my finite element model. And in order to do that, I'm going to collect a data set of input-output pairs based on the parameter values that I've estimated for the inverse problem. So this is why I was saying that if you have some observational data, you can start to solve your inverse problem to estimate some parameters that are of interest. That parameter of interest, you can solve your FE model with, and then that's the data that you use to train your surrogate model. And then that then goes back to the data fit problem. So it's kind of this nested problem where you estimate the parameters of interest a little bit. You use that to query your finite element model, train your surrogate based on this, and then you adjust and you keep going back and forth. So what you end up having is this collected data set that adaptively changes based on what your estimate of the relevant parameters that are there. Yes. Okay. Okay. Thanks for continuing with it. No. I think I agree. Like I'm quite familiar with the notation by now, but some people aren't as well, so it can make things a bit obscure sometimes. Thank you.
Any further questions? Otherwise, I'm going to jump in. In the follow-up to that, at the moment we do also a process, essentially a two-step process. And I've tried to do the inverse problem first without a surrogate, which takes a long time.
Yeah.
But essentially start with, or actually start with kind of a semi-informative set of priors, train a conventional surrogate. But what I found is then the eventual inverse problem becomes tied to the accuracy of the surrogate.
Yeah.
Because it's now just seeing what the prior distribution parameters it tells it, and it's very good for that. But because it's a distribution, it's also much better at things closer to the center than the edges. Whereas for an inverse problem, obviously you don't know. How do you solve the issue with that two-level approach?
So essentially, in a nutshell, what we're doing here is we're doing that kind of procedure where you're first posing a distribution. Maybe you query it at a few points with your, and then solve it with your finite element model, and that allows you to train a surrogate. But the idea is that we basically do that iteratively, and we keep swapping back and forth between the two problems. And when we try and add to like our data set to train our surrogate model, we don't do 1,000 every time. You just add a few extra samples that are drawn from this new estimate from the underlying distribution, and then you just train your surrogate model for maybe 100 steps or something, and you just update it slightly based on that, and you go back and forth between the two repeatedly very fast, and that allows you to continuously adapt your surrogate model to track the inverse problem that you're trying to solve at the same time.
You also went and showed us kind of how more observations of different systems helps this inverse problem, the methodology. What you have lots of systems to observe, but each one you have very sparse observation, which sometimes is the case in, say, geotechnical problems, where what you're trying to observe, you only have very, very limited essentially observations of any one particular system.
Yeah.
Are the ways out of.
So basically, this part of what we developed this methodology for was to address those kinds of problems where you've got possibly low quality, not immensely informative data on a per physical system basis. So if you tried to learn something about one particular physical system, you'd be in a bit of a bad position. But because you're essentially collating information from so many physical systems, you're kind of like triangulating the inverse problem across many different physical systems to reduce, to improve your accuracy and the estimate of your parameters. So that's kind of what we've seen this methodology do best with. Yeah.
And then the final thing was that physical system, we're still assuming our mathematical model of it is almost perfect. But again, in a lot of infrastructure models, especially in geotechnics, we aren't able to create perfect PDs or PD solver. Our description of something being elastic isn't actually truly elastic. It's far from it. It's very non-linear. We can't, even with our best attempts, come up with the models deterministically. We can't have I see that you've got a way to decouple the noise from the model, but if that noise is non-Gaussian, if that noise actually is model error, that's systematic. What are some ways we can?
So I've got some work with a student that was looking at essentially trying to do these kinds of problems where you have to a parameter inference problem. You're obviously trying to learn a surrogate as well to accelerate the computation, but there's also a part of the equations that is not well understood, that is not known, something like a closure model. And the idea in this work was to essentially parameterize that with a neural network and try and incorporate that in the framework and see if that works. And we have found some success on a certain class of problems of interest where you have these nonlinear PDEs, and the nonlinearity in the PDE is actually not well understood. And so you try and directly learn what is a good fit approximation to the nonlinearity that's present in your model. So the idea here is to kind of combine partial model knowledge with these small extra bits of flexible parameterizations that you can try and jointly learn in your inference problem. I don't know if that kind of approach could be helpful in the scenarios that you're describing. But here there'd be quite a lot of physics that you understand. So you know the conservation of mass, you know that it's roughly looking like elasticity, but maybe there's a slight nonlinear component to it, and you just want to learn that nonlinear component with maybe it's a 1D relationship between stress and response and something like that. And that seems these kinds of methods that look at data coming from lots of physical systems seem to perform quite well in that condition, because you're triangulating across lots of physical realizations to actually hone in on what is a single possible model for that nonlinearity. So that could be something that goes in that direction.
Final comments or thoughts? Right, thank you very much.
Thank you.
So yeah, such a nice overview.
Yeah, it was. Yeah, I never know whether or not the deep dive talks are better, or is it better to do overview? It's yeah.
Great.
I can...
Stop the recording. That's all.